Okay, chapter 4 is still about series, but we are more specific on power series. So what does it mean by power series? Okay, a power series about the point x node is an expression of this form where we have summation of an multiplied with x minus x node to the power of n, and this one can be expanded into the expanded version lah. So if you try to expand, this is the terms when n equals to 0, n equals to 1, n equals to 2, and so on. So you can try to recheck on this. Okay, so this kind of power series converges at point x equal to x node if the infinite series converges. Okay, sorry, this is if. Okay, that is when you find the limit as the big N goes to infinity for the series n from 0 to the big N for the an x minus x node to the power of n, you found out that the limit exists to a certain number and it is a finite number. So the power series is converged. But then if the limit does not exist, so the power series is said to diverge at x equals to x node. So when the limit exists, the power series converge, but if the limit does not exist, then the power series diverge. Okay, let us look at the radius of convergence, or this one can be symbolized as the symbol of rho. Okay, theorem 4.1. For each power series of the form of equation 4.1, there exists rho from 0 to infinity. Okay, that is called as the radius of convergence of the power series, such that equation 4.1 converge absolutely, okay, for the absolute of x minus x node lesser than rho, which is the radius of convergence. Okay, and it diverges for the absolute x minus x node greater than rho, which is the radius of convergence. So converge absolutely for the case it is this one is less than rho, and diverge if this one is greater than rho. And then if the series 4.1 converge for all value of x, then rho is equals to infinity. Okay, as it converge for all value of x, so means that the radius of convergence is just everywhere. So rho is equals to infinity. And when the series converge only at x equals to x node, then rho is equals to 0. Okay, so to determine the radius of convergence rho, we can use the ratio test method. Okay, ratio test method. Okay, so let us look at the ratio test for this power series. So if for large n, the coefficients an are non-zero, satisfying this limit. So we take the limit n goes to infinity, we take the absolute of an plus 1 divided by an equals to L. L can be from 0 to infinity. Then the radius of convergence, or the rho of the power series of this power series is rho equals to 1 over L. Rho is equals to infinity if L equals to 0. Okay, and the rho is equals to 0 if L equals to infinity. Okay, like this. So when you find the limit by using ratio test, you find what is the value of L, right? Okay, and then you need to find what is rho. So you know rho is equals to 1 over L. Okay, so it says here that if rho is infinity, okay, means if I just plug in lah, rho is infinity somewhere here, 1 over L, then for sure this L should be 0 in order for us to get the rho infinity. So that's why if rho is equals to infinity, then L equals to 0. So the same thing, if rho is equal to 0 if L is equals to infinity. Okay, so rho equals to 1 over L. Okay, if L is equals to infinity, then 1 over infinity, you know your rho is 0. Okay, so that is what it's meant by this statement. Okay, remark 4.1. We caution that if the ratio does not have a limit, then methods other than the ratio test, like the root test, must be used to determine rho. Okay, in particular, if infinitely many of the ANs is equals to 0, then the ratio test cannot be applied directly. So we can use another test like the root test instead of the ratio test in order to find the limit, in order to check the convergence, and from that we can find the radius of convergence. Okay, let us look at example 1. Okay, example 1, maybe we can do this again instead of showing you. Okay, so I copy this first. Macam mana nak copy tu, tak apa, it's okay. So I wrote it back for you. So example 1, we have the series. Then we need to find the radius of convergence and the interval of convergence. So we have power series. So we want to find radius of convergence. So to find the radius of convergence, we need to find first, is it the series converge or not? And then the interval of convergence. Okay, so first we find, we check first if the series is converge or not. Okay, that is by using, we use this one. We take the limit. We use the ratio test. So limit n goes to infinity. Okay, an plus 1. So which one is the an actually? The an is this one. Okay, so for the case of an plus 1, then what we have is 2 to the power of negative n plus 1. Okay, over n plus 1 plus 1. Okay, so the an here is the, this is just the an. So what happened for the an plus 1, then we replace lah the n as the n plus 1. Like this. Okay. And then divide by an, just an, which means the original one. Okay, don't forget your absolute. Okay, now you can rearrange to make it looks more simpler. So what you have is, okay, I skip certain part. Okay, 2, negative n, 2, 1. Okay, multiply with n plus 1 over, okay, n plus 2 multiply with 2 negative n. Okay, and then absolute. Okay, so from this one, you can cancel out the terms of 2 to the power of negative n. Okay, so I continue right here. 2, negative 1, n plus 1 over n plus 2. Okay, or you can rewrite back as n plus 1 over 2n plus 2. Okay, because you can bring this one, 2 to the power of negative 1, you can bring it at the denominator, then the power of negative 1 would be removed lah. So this how it looks like. Much more simpler. Okay, and then you can solve for the limit. Okay, you can divide by the n, or you can factor out the n, or you can apply the L'Hopital rules. Okay, so at this part, I think I would just remove the absolute or the modulus. Okay, because we know the value would always be positive. Okay, even there is no absolute. So I write it as this one without absolute. So I just expand the denominator, it becomes 2n plus 4. Okay, so now you can solve for the limit. So this one 4 divided by n. Okay, so you know this is 0. This is 0 and then the limit is 1/2. So 1/2 is the L. Okay, now you already have the L, so now we can find what is the radius of convergence. So you know radius of convergence, it is rho equals to 1/L. Okay, so in this case what we have is L is 1/2. So 1 divided by 1/2. Then you get the rho is equals to 2. Okay, this is your radius of convergence. Okay, now we need to check on the interval of convergence. Okay, how to check on this? So we come back to the theorem. Okay, so it says that the power series converge absolutely for the case of x minus x naught in the absolute lesser than rho, and diverge if it is greater than rho. So we apply this inequality. So what we have is, okay, check convergence interval. So it says that, okay, the series is absolutely converge, okay, when x minus x naught inside modulus is lesser than radius of convergence, which is the rho. So in this case, okay, in this case you need to recognize what is your x naught. Okay, so in this case your x naught is actually this one, yeah. This is x naught. So means that x minus 1. Okay, we write it back. X minus 1 less than rho is 2. Okay, so now you can try to expand this absolute. So it becomes x minus 1 lesser than 2 and greater than negative 2. So x is lesser than 3, greater than negative 1. Okay, you can try to look at the line interval for this one. Okay, let's say you have x naught here. Your x naught is 1. X naught equals to 1. Okay, and then okay, this is 2, this is 3, this is 4. Then 0, negative 1, negative 2. Okay, so it says that it is absolutely converge when x is in between 3 and negative 1. 3 and negative 1. So means that this is where the power series converge at x from negative 1 to 3 converge. Okay, and also you know that the radius of convergence is rho. So this rho means that, okay, since your x naught is here, so from the x naught to negative 1, you know that this is the distance is 2, right? Because the radius, okay, the radius from the origin to negative 1, which is the somehow the last term of the interval for the convergence to negative 1 is 2. Okay, 1 and then 2. Okay, the same goes for the other side. So 1, 2. So you know this is rho. Okay, another thing before we go to the diverge part, but we can still look the diverge part through this line interval. Okay, since you know this is the convergent part, then for sure the rest of the interval is the divergent part, which is from here to infinity. Okay, and then from here to negative infinity lah. So this is the diverged part. Okay, but then how can we find the diverged part algebraically? Okay, so since we have by the theorem, we know that the power series diverge when x minus x naught greater than rho. So what we have for this power series, x minus 1 greater than 2. So you can expand this one. So we have x minus 1 greater than 2, and then x minus 1 is lesser than negative 2. So from this one, you will obtain that x is greater than 3, and this one is x is lesser than negative 1. Okay, but then we need to also check, since we already know the interval, we need to also check, does this one is just lesser, or it is also equal to negative 1. The same goes for this one. Is it x in between in between 3 and negative 1? So does it this 3 included or not? Does it negative 1 included or not? Okay, we don't know that. The same goes for this one. Is it x just greater than 3, or x greater equal to 3? Okay, and does it x lesser than negative 1 or equal to negative 1 as well? So we need to check on this. Okay, so by we need to check this by substitute back the value of the x inside the original power series. Okay, so since we have x minus 1 equals to 2, which is the rho, radius of convergence, so hence we know that the 2 can be either positive or negative in order for us to remove the absolute. So hence x minus 1 can be equals to negative 2, and also x minus 1 can be equals to 2. So for this case, okay, we would get x is equals to negative 2 plus 1 is negative 1, and then this one is x equals to 3. So we need to check at these two conditions when x equals to negative 1 in the original power series, and also for the case when x equals to 3, we need to check, is it the series converge or not? Okay, so if it is converge, then for the case of the interval on the convergent, it is just not lesser or greater, but then it is also lesser and equal, or greater and equal. Okay, let us try for the case x equals to negative 1. Okay, so since our original series is our original series is n from 0 to infinity to the power of negative n over n plus 1 x minus 1 n. Okay, so the x that we want to substitute, this one lah. So we substitute this x as negative 1. Okay, then so you would obtain 2 to the power of negative n over n plus 1. So negative 1 minus 1 to the power of n. This gives you negative 2 to the power of n. Okay, so now you need to check the convergence of this series. Okay, this one is related back to chapter 2. Okay, if you have this kind of series, what kind of test that you can use? Okay, so before that, I would like to simplify this series first. Okay, so to make it simpler, 2 to the power of negative n, this one I want to put it at the denominator. So the power of n would become just n, not negative n. So negative 2 to the power of n divided by 2 to the power of n and then n plus 1. Okay, so now you can simplify again. Okay, this can be negative 2 divided by 2 to the power of n. Okay, 1 over n plus 1. So negative 2 divided by 2 is negative 1. So negative 1 to the power of n over n plus 1. Okay, if you look at this, you know this is somehow the alternating series because it has the form of negative 1 to the power of n. So we can try to use the alternating series test to check. So recall back the first condition to test the power series. Okay, you need to recognize what is the Bn. So in this case, the Bn is 1 over n plus 1. Okay, so you need to check on the two conditions. Bn should be decreasing and the limit of Bn should equals to 0. Okay. So to check the decreasing, I let Bn as a function first. And then I find the derivative. So the derivative for this one is negative 1 over x squared. So you know when you plug in whatever value for the x, it would gives you a negative value. Okay, so means that Bn is Bn plus 1 is Bn plus 1 is decreasing, is greater than Bn. Bn plus 1 is lesser than Bn. Okay, which means it is decreasing lah. Okay, so this series decreasing. Okay, second condition, you check the limit for Bn. N goes to infinity. That is the limit for 1 over n plus 1. So you know this one, you can directly plug in the n as infinity. So infinity plus 1 is infinity. 1 divided by infinity is 0. So therefore it fulfills the second condition as well. And we can conclude that the series is converge. Okay, this is for the case x equals to negative 1. Okay, recall back our interval for convergent. Okay, this one. Okay, I paste it here. So means that means that this part, okay, it should be x greater and equals to negative 1. Because at the x equals to negative 1, we found out that the series is also converged. So negative 1 is also included. Okay, then we check for this one. Is it x lesser than 3 or x lesser and equals to 3? So we check x equals to 3. Okay, and then we substitute 3 inside the original power series. So we plug in x equals to 3 here. Okay, then what you will obtain, 2 negative n over n plus 1. So 3 minus 1 is 2, you get 2 to the power of n. So again, we can simplify first. So I put the 2 to the power of negative n kat bawah. So what we have is 2 to the power of n divided by 2 to the power of n. multiply with n plus 1. Okay, so you can cancel out the 2 to the power of n, 1 over n plus 1. Okay, this kind of form, I think we can choose to use the comparison test. Okay, but for that, maybe we can use the limit comparison test. Okay, if you look at this series, this is nearest to the form of series 1 over n. So you know the series of 1 over n is divergent series. Okay, if you use the limit comparison test, okay, limit comparison test, that is you find the limit and goes to infinity, un divided by vn. So in this case, our un is, this is un and this is vn, the things that we want to compare with, the things that we choose to be compared, okay, with our series. So in this case, okay, since we compare with a divergent series, if you get the limit is greater than 0, okay, then we can conclude the limit that we have also divergent. Okay, so let us plug in. So un is our series 1 over n plus 1 divided by the things that we compare, which is 1 over n. So you simplify. Okay, so this one becomes n over n plus 1. Okay, you find the limit. You can factor out the n. Okay, cancel out, this become 0. So you have is 1 over 1, which is 1 greater than 0. So therefore, since Vn, that is summation 1 over n, diverge, and the limit of un divided by Vn is equals to 1, which is greater than 0. Okay, hence the series also diverge. Okay, since at the x equals to 3, the series diverge. Okay, so I copy back this one. Okay, so therefore at the x lesser than 3 is just x lesser than 3. So the interval of convergence, or the interval of convergence, betul. So the interval of convergence, this one lah, is from x lesser than 3 and x greater and equal than -1. So you can also write this one as -1, 3. Okay, the interval of convergence. So what about the interval of divergence? You can find out by just looking at this interval of convergence, which is the other way around lah. So the interval of divergence can be from -infinity to -1, and 3 included, 3 to infinity. Okay, this is for, but the question just asks for the interval of convergence, which is this one. Okay, example 2. Let us try example 2. So example 2, you need to find the same thing, radius of convergence and the interval of convergence. Okay, so the given series is 2 to the power of n divided by n factorial x to the power of n. Okay, so to find the radius of convergence first, okay, we find the limit. Okay, for an plus 1 divided by an. Okay, so based on the given series, what you have is for an plus 1 is 2 to the power of n plus 1. Okay, divide by n plus 1 factorial. Okay, divide by an, which is 2 to the power of n factorial. Okay, this is too long. Okay, so now you can rearrange first. So it becomes 2 to the power of n plus 1 multiply with n factorial divide by n plus 1 factorial multiply with 2 to the power of n. Okay, and then this one you can expand it a bit because you want to cancel out something. Okay, so that we can solve for the limit. So 2 to the power of n plus 1 would become 2 to the power of n multiply with 2 to the power of 1 multiply with n factorial divide by, okay, for this one, okay, I just let it to be n plus 1 factorial first, but then we need to do something on that. Okay, at this point you can cancel out 2 to the power of n. Okay, so what's left is 2 multiply with n factorial divide n plus 1 factorial. Okay, at this point you know you want to solve for the limit, but we don't want the factorial to be there. So what we do is we expand. We try to cancel out the n factorial at the numerator. So I want to expand the n plus 1 factorial at the denominator. So if we expand this one, it would be n plus 1 multiply with n plus 1 minus 1 factorial. That is just n factorial. Okay, so now we have n factorial at the numerator and denominator, then we can directly cancel out. So cancel out, cancel out. So what's left is 2 over n plus 1. So I remove the absolute because we know that that the things inside absolute will always be positive lah. But if you want to still consider the absolute, then it's okay. Consider until the end pun boleh. So this one you can solve for the limit. So like to factor out the n. So n1 plus 1 over n. So you know this one will become 0, 0. Okay, this one cancel out. So 0 divided by 0 divided by 1 is 0. So 0 is the L. Okay, so you want to find the radius of convergence, you know rho is equals to 1 over L. So in our case right now, the L is 0. So if L is 0, that means your rho should becomes infinity. Okay, so means that the radius of convergence for this series is infinity, and therefore the interval of convergence is negative infinity to infinity. So you might want to refer back to the theorem. Okay, so since the radius of convergence is infinity, the radius is just everywhere at all parts, means that this series is converge at any value of x, and there is no divergence part. So therefore the interval of convergence is from negative infinity to infinity. Okay, you can consider this directly lah. Okay, next we look at example 3. Okay, in this form, so we know this long kind of form, we recall back to chapter 3. So this form can be translated into a series form, right? So from this you need to recognize lah, okay, what kind of series form for this ln 1 plus x divided by 1 minus x. So you need to look back at the chapter 3. Okay, let us try example 3. So it gives okay, this one. So based on chapter 3, you have found this. You have tried to find what is the series for this one. It is equals to 2 summation 0 to infinity 1 over 2n minus 1 x to the power of 2n minus 1. Okay, so this is the series. So again, you want to find the, okay, what's the question asked? Radius of convergence. Okay, so you want to find the radius of convergence, then we find the limit. For en plus 1 divided by en. Okay, so this one, en plus 1 becomes, okay, before that, recognize first which one is en. So the en is this one. Okay, like the previous example, where is the en? En is this one. So what we have is 2 divided by 2. Okay, 2n plus 1 minus 1. Then divide with 2 over 2n minus 1. Okay, so you rearrange first. So 2 multiply with 2n minus 1. Divide with, okay, I expand directly, so it becomes 2n plus 2 minus 1, and then multiply with 2. Okay, simplify first, you get 4n minus 2 over, okay, or maybe you want to directly cancel out lah the 2 and 2. So you have 2n minus 1 over 2n plus 1. Okay, so you can solve for the limit. Cancel out, this one becomes 0. This is also 0. So you have, what's left is just 2 divided by 2. Okay, I read it full lah. 2 divided by 2, and then you will get, it is 1. So 1 is the L. Okay, so rho is equals to 1 over L, and our L is 1, so 1 divided by 1 is 1. So rho is equals to 1. Okay, that is example 3. Okay, we look at this theorem 4.3. If the power series is equals to 0 for all x in some open interval, then each coefficient en is equals to 0. So meaning that for the power series to be equated, to be equals to 0, okay, for this, okay, let us look at this lah directly. Contoh, for example, you have this form, okay, an x minus x naught equals to 0. For this thing to become 0, it is either en is equals to 0, or this part to become 0. But in this case, that we know that we want a power series. We know that it is power series. If this part equals to 0, then it's not called as power series anymore. Okay, so instead of this one equals to 0, then we can see that supposedly en is equals to 0 for the power series to become 0. Okay, so just keep this in mind. Okay, because we would use this on the next part. Okay, properties of power series. So given two power series, fx and gx, okay, so we have the sum or the difference of the power series can be written this way. Okay, so okay, this is your en, and this is Bn. Okay, but before that, I want you to recognize. Okay, between these two power series that we symbolize or we name it as a function. Okay, so you look at this. This part should be the same. Okay, in order for us to apply the properties of power series. Okay, then we can apply the sum or difference of the power series as this one. So for the sum or for the difference, you can write between these two series like this one. Okay, and for the product, okay, you can okay, this is the same thing lah for both series. You should have the same thing. Okay, and then this is for the first power series. Then this is second power series. Okay, so you need to find the product. So you expand one by one. Okay, so this is for En, from En for sure. Oh, tu salah color. This one, okay, this one should be yellow. Okay, you can try to expand. How can this form become this form? You can try to expand. Okay, and then this expanded version can be rewritten as a new form of power series that we call this Cn as the Cauchy product. Okay, that is this Cn is equal to this form of series. Okay, it can be generalized this way for the Cn. Okay, and then for the quotient, we have also the Cauchy quotient. Okay, instead of the Cauchy product. Okay, we hold on this part first. Okay, we continue on the next theorem. The next theorem is about differentiation and integrations of the power series. So if the series, okay, looks like this, the power series lah, has a positive radius of convergence. Okay, remember this, has a positive radius of convergence. Then this f, which is the series, is differentiable in the interval of absolute x minus x naught less than rho, which is the interval of convergence. And termwise differentiation gives the power series of derivative of f. Okay, that is, so when you differentiate this power series, of course you bring this n to the front, okay, the power kan, and then you minus the power with 1. So that's why here what we have is we multiply with n and then we minus the power with negative 1. Okay, that is for differentiation. For integration, almost the same. Okay, so when you integrate the power series, you would plus 1 the power. Okay, and then you divide with the power n plus 1. Okay, for x minus x naught, absolute of x minus x naught less than rho lah. So in order to apply this differentiation and integration of power series, the radius of convergence should be positive. Okay, it is only applicable if the radius of convergence is positive. Okay, let us try to look at this exercise 1. Okay, determine the radius of convergence and interval of convergence for this power series. So what we have is series is 2 to the power of n divided by n, and then we have 2x minus 6 to the power of n. Okay, we have this kind of series. Okay, but then at this series, if you recognize this part, okay, compare to the one that we have done on the example. Okay, on the example, we have this kind of x to the power of something. Okay, so x stand alone as x. Okay, this one too. The x stand alone as the x with its power lah. This one too. X is just x minus 1. Okay, but for this exercise, you see that it is 2x minus 6. So means that you need to make some adjustment on the power series first before we can proceed on finding the limit and then the radius of convergence. We need to make the x alone. Okay, so from here you can equal lah. So you can adjust. How can we adjust to make the x alone? Okay, so we can factor out the 2. So we have 2 multiplied with x minus 3 to the power of n. So from this one, we can separate 2 to the power of n divided by n, and then 2 to the power of n multiplied with x minus 3 to the power of n. So now the x is just on its own. Okay, so you can, now you can directly find the limit. So limit, okay, before that you know that the an is this part. Okay, so the limit n goes to infinity, an plus 1 divided by an. So this one, based on the given series, it becomes 2 to the power of n plus 1 multiply 2 to the power of n plus 1 divided by n. Okay, and then divide by 2 to the power of n, 2 to the power of n divided by n. Sorry, this is n plus 1. Okay, so we put the absolute. So I want to rearrange first instead of expanding. So we have 2n plus 1, 2n plus 1 multiply with n divide by 2 to the power of n multiply 2 to the power of n multiply with n plus 1. Okay, now then I want to expand. So 2 to the power of n, 2 to the power of 1, 2 to the power of n, 2 to the power of 1, n divided by 2 to the power of n, 2 to the power of n, and then n plus 1. Absolute. Okay, and then you can cancel out 2 to the power of n with this one, and then this one with this one. So what's left is 2 to the power of 1 and 2 to the power of 1, so you get 4 lah. So 4 divided by n plus 1. So then you can solve for the limit. Oh, sorry, this one is for n. So n 4 divided by n, 1 plus 1 over n. Okay, so you cancel out the n. So 4 divided by 1, so 1 over, okay, this is 1 over n. Okay, this one should be 0. So 4 divided by 1 would becomes 4. Okay, so the limit is 4. And then you know that the rho is 1 over L. So therefore, rho is equals to 1 over 4. Okay, this is the radius of This is the radius of convergence. And then you want to check for the interval of convergence. Okay, I write it here. Check convergence interval. Okay, so we know that we have two okay, so convergence interval. So we know that The convergence interval is initially look like this, x minus x naught less than rho. So in this case, our x naught is 3. So x minus 3 less than rho is 1 over 4. So from this, we know that x minus 3 is less than 1 over 4 and greater than negative 1 over 4. So x is in between 13 over 4 and 11 over 4. So now you want to check this inequality. Is it has the equal sign or not? So to check on that, like the previous example, so we check first for the case when x equals to 1 over 4. Okay, so you plug in 11 over 4 into the original series. Okay, so we would get 2 to the power of n over n. Okay, and then so 11 over 4. Okay, so you plug in x dekat sini lah. X dekat x yang ni. So that part you would get negative 1 over 2 to the power of n. Okay, so now we need to check the convergence of this series. So this one can be rewritten to make it easier for us to check for the convergence. This one becomes, okay, 2 to the power of n over n. So negative 1 over 2 to the power of n can be written separately, which is negative 1 to the power of n over 2 to the power of n. Okay, now you look at this, you can cancel out this 2 to the power of n, and what's left is negative 1 to the power of n over n. Okay, looking at this, you know that you can apply the alternating series test. So we use the alternating series test, which means your Bn is 1 over n. Okay, first you want to check the decreasing. Okay, I let it as a function. So 1 over x. So the first derivative is negative 1 over x square. So it is decreasing. So this series is decreasing. Second condition, we find the limit n goes to infinity for 1 over n. So 1 divided by infinity would become 0. So it also fulfills the second condition. Okay, so therefore the series converge. At x equals to 1 over 4. Okay, and then we check at x equals to 13 over 4. Okay, so we plug in x as 13 over 4 inside the original series. Okay, then you would get it becomes 1 over 2 to the power of n. Okay, so this one you can adjust first a bit. So I just separate it. So 1 to the power of n divided by 2 to the power of n. Okay, and then you can cancel out this 2 to the power of n, and what's left is, okay, 1 to the power of n. So you find 1 to the power of any number, it would always be just 1. So therefore you can just write it as 1. Okay, and then the denominator 2 to the power of, sorry, denominator is n. Okay, 2 to the power of n dah cancel out. So you have this series. Okay, looking at this series, you know that okay, as in chapter 2, you know that this kind of series you would always use to compare about the divergence. Okay, you know this is a divergent series. Okay, so therefore since this is a divergent series, okay, so we can conclude that the interval of convergence is, okay, since for 11 over 4 it is converged, That means we have equal sign at this part. Okay, but for the 13/4, it is divergent. Then it's just x lesser than 13/4, because this is about the interval of convergence. We only care about the convergence. Okay, so this is the interval of convergence, or you may write as 11/4 and then 13/4, open bracket. Okay. Okay, since this is the interval of convergence, then you know for the divergence, kalau interval of divergence interval, it would become the other way around lah, which is negative infinity to okay, I think there is some typo. Okay, betul-betul. So for the divergence, negative infinity to 11/4, not including, because for divergence, and also including 13/4, because 13/4, you know, it is divergent to infinity. Okay, but then the question just asks about the interval of convergence. Okay, so this is the interval.